Okay, so I guess before we get back into that, quiz 2 is on Monday. So remember, for these quizzes, there's no problem solving. It's just reading your notes, remembering stuff from the notes. It's just my way of getting you to go back through your notes periodically. We have to do a few more quizzes in the last, I guess we have a month and a couple weeks or whatever. We're going to have to pick up the pace of these quizzes. And remember that these are all cumulative. So that just means you have to go back to the beginning and read through. Any questions about the quiz? Okay, so here's what we're working on. Bless you. We have this 4-bar linkage. These angles are 30 degrees. The lengths of all of these members are 1 meter. And this is also 1 meter. The masses of each of those 3 members are 5 kilograms. The externally applied force, you can think of this as by some motor, is 100 Newton meters, couple. And if we label these bodies 1, 2, and 3, and the joints A, B, C, and then I'm calling this one P. We want to find the acceleration of that point P. And what we finished last time was the rigid body analysis of each of those 3 members. And we came up with, so we're done with the rigid body analysis. And we came up with 5 equations from that. And those are negative 0.5 F12x minus 0.866 F12y minus 1.6 repeating alpha 1 is equal to negative 21.24. The second equation is negative F12x plus F23x minus 5A2x is equal to 0. The third equation, negative F12y plus F23y minus 5A2y is equal to positive 49.05. 2 more to go. The fourth equation says 0.5 F12y plus 0.5 F23y minus 0.416 repeating alpha 2 is equal to 0. And then the last one that we have so far from the rigid body analyses is 0.5 F23X plus 0.866 F23Y minus 1.6 repeating alpha 3 is equal to 78.76. Okay, and how many variables do we have? Well, first look at the problem and figure out how many variables we should have based on the number of constraints we're going to need. What joints are going to need constraint equations? We don't need them in A or C because those are fixed. We do need them at P and B. Okay, we need to say that these two members agree on the acceleration at that point, and these two members agree on the acceleration at that point. Okay, so how many constraint equations do we get at here and here? Four, yep. X and Y components of acceleration. So if we have 5 equations, we're going to have 4 constraint equations. How many variables would we expect to see if we count the variables in these 5 equations?
9.
Yeah, well, right, we expect to see 9 variables so that when we take these 5 equations and the 4 constraint equations, they add up to the number of variables. So let's just check that real quick. So the variables are F12, X and Y components, alpha 1, F23, X and Y components, A2, X and Y components, alpha 2, and then the only one left is alpha 3, I believe. So that's 2, 4, 6, 7, 8, 9 variables. Okay. Any questions about that? So the next step is to go to these constraint equations. And let's first start with that constraint equation at P. Okay, we have to calculate the acceleration of P according to member 1, calculate the acceleration of P according to member 2, and then set those two equal. So I'll pause this and take a few minutes and see if you can come up with that pair of constraint equations at P. Okay, so we're doing the constraint at P, and I'm going to calculate the acceleration of that point P according to member 1 first, and then member 2. For member 1, that point P is just in circular motion around A. So we're just going to say the acceleration at P is equal to watermelon equation. We're assuming that this is at rest at this instant. It's starting from rest. So the centripetal acceleration term goes away because those omegas go away. This alpha vector is 0, 0, alpha 1. And that R vector, remember the definition of R is the vector from the center of the circular or spherical motion to the point that you want. So this is the vector from A to P. So that is going to be negative 0.866, positive 0.5. And so the acceleration of P according to member 1 is 0, 0, alpha 1, crossed with negative 0.866, 0.5, 0. And what do you get for that? Negative 0.5 alpha 1. And then negative 0.866 alpha 1. Anyone get something different? So for the x component, you got 0 times 0 minus 0.5 alpha 1, so that's good. And then for the y component, cross that out, 0 times 0 minus alpha 1 times negative 0.866, and then the negative of that because it's the y component.
Okay.
Yeah. Y always has to be the difficult one. And all right, so now let's go to member 2. And this time we have to use relative motion because there's no fixed point. So we're going to do the acceleration of P according to the ground, relative to the ground, is equal to the acceleration of P relative to the center of mass of body 2, plus the acceleration of the center of mass of 2 relative to the ground. This one, we already have a different name for. This is A2, and those are variables we've already defined. And this one is circular motion around the center of mass of 2. So this is the watermelon equation. Okay, so the acceleration of P relative to the center of mass of 2. This goes away because our omegas are 0. Our alpha vector is 0, 0, alpha 2. And R goes from the center of the circular motion to the point we care about. Well, in this case, the center of our circular motion is the center of mass of body 2. And so the R vector is in the negative x direction, half of the length of that member. So it's just negative 0.50. So this is 0, 0, alpha 2. Crossed with negative 0.500. And you get 0 for x. And for y, you get negative 0.5 alpha 2. Now don't forget about the relative motion. So the acceleration of P relative to the ground is 0, negative 0.5 alpha 2, I'll just write it as 2 components, plus a2x, a2y. So a2x, and then the y component is negative 0.5 alpha 2 plus a2y. And so finally, the constraint equation says negative 0.5 alpha 1 negative 0.866 alpha 1 is equal to a2x negative 0.5 alpha 2 plus a2y. And these are equations 6 and 7. So 6, I'll write this as negative 0.5 alpha 1 minus a2x is equal to 0. And equation 7 says negative 0.866 alpha 1 plus 0.5 alpha 2 minus a2y is equal to 0. Bless you. These constraint equations, do they always have constants equal to 0? Can you imagine where those constants would come from? Yeah, if you have omega, right. If there's a non-zero omega, then you'll get constants due to that because those are not variables. Those have to be given. Okay, and now moving on to the constraint at B. So take a few minutes and see if you can come up with the constraint requiring that members 2 and 3 agree on the acceleration of B. Okay, so we're going to do this according to member 2. Member 2 doesn't have a fixed point, so the acceleration of B relative to the ground is equal to the acceleration of B relative to the center of mass of 2 plus the acceleration of the center of mass of 2 relative to the ground. This is A2. And this is the watermelon equation. So the acceleration of B relative to the center of mass of 2 is equal to alpha cross R plus omega cross quantity omega cross R. This is all 0 because we were given the omega is equal to 0. The alpha vector is 0, 0, alpha 2. The R vector, that is the vector from the center of the circular motion to the point we care about. The most predictable, like take this to Vegas, fact about quizzes in this whole class is I'm going to ask these 2 questions at least once on these quizzes. Each of these. Okay. The first one is, what's the definition of the R vector in the watermelon equation? Okay, that needs to be front and center in your brain because sometimes these problems can turn you around. You need to have that, to fall back on. And the other one is the definition of the row vector in calculating those moments. Okay. And then the R vector for this one, this is the vector from the center of, from the center of mass of body 2 to that point B. So this time that's positive 0.500. And so the acceleration of B relative to the center of mass of 2 is 0, alpha 2 crossed with 0.500. By the way, if you have a TI-89 or a TI Inspire, it'll let you do these cross products with variables in there. If you have an 84, an 83, or an 86, I think you just have to do it by hand or use MATLAB or whatever. But okay, so this is 0 for X, and then positive 0.5 alpha 2 for Y. And so the acceleration of B relative to the ground is this plus this. And I'll just combine it all. Okay, and then I guess the easier one is according to member 3. This one we don't have to use relative motion because there's a fixed point. We just have to use circular motion. So the acceleration of B is just the watermelon equation.
It should be the same. Water. Yeah, with a different.
Yeah, right, except it's a different alpha.
Yeah.
Yep. So alpha is 0, alpha 3. R is 0.866, 0.50. And so the acceleration of B, this is all 0. 0, alpha 3. Yes, thank you. Crossed with negative 0.866, positive 0.50, and that is positive 0.5 alpha 3. Nope, that's negative. And then negative 0.866 alpha 3. Everyone agree with that? And so now we'll set these two equal to each other. So we have A2x 0.5 alpha 2 plus A2y is equal to negative 0.5 alpha 3, negative 0.866 alpha 3. And so our last two equations, equation 8 says A2x plus 0.5 alpha 3 is equal to 0. And our ninth equation says 0.5 alpha 2 plus A2y plus 0.866 alpha 3 is equal to 0. we already knew we had 9 variables. Now we have 9 equations and we can solve this. So now take a couple minutes and solve this equation. Well, I got F12 is 93.95, negative 29.29. Anyone get that? No? Damn it. Okay, what?
Mine failed, so.
Oh,
I got negative 5.2 times 10 to the negative fifth
okay.
1x and negative 15.09.
Anyone get 0 and 15? I'm going to write down what I got then, because I'm great at this. Then F23, 99.45, 29.29. Then alpha 1, negative 2.2. Then alpha 2 is 0. Well, that's one thing you need to get that alpha 2 to be equal to 0, as people pointed out before we started this problem. You can see that from the geometry, so that's a good sign.
Alpha 3 should equal alpha 1, correct?
Yeah. And I got that, so negative 2.20. And then the acceleration of body 2, I got 1.10, 1.91. The units, so the forces are newtons. The angular accelerations are radians per second squared. And the acceleration of the center of mass of 2 is meters per second squared. Okay, if nobody else got the same stuff, we'll just go with these.
I mean, that looks right. I mean,
Looks reasonable.
A3 is equal to A1. So,
Mm-hmm.
so if you're ever doing a problem, because if you look at it, geometry-wise, I can
Right.
tell that A1 is going to equal to A3.
Yeah.
Would you ever dock points if we see something like that and we're shortening?
You know, on a test, for one thing, on tests, I tend not to make you solve the sets of equations because, like, there's just so many places you can enter something wrong. But if I ever did make a simple problem and you got answers that didn't make sense to you, just jot that down as a note, you know, just so I know that I don't want you to go back and try to fix it if under short time or whatever, but anything you notice, just let me know that you notice it, you know. Because I grade all these problems just like sort of, I don't take 1 point off for one mistake, 2 points off, you know. I'm just like looking at everything you do and then I'm saying out of 6, how well does this look, how good of an understanding of this problem am I seeing here, you know? So show me what you know, you know.
Yeah, because technically, this is something just I'm looking at. Like, in order to shorten it, I could just do A4 my 8
Mm-hmm.
9 equation. Couldn't I just say I can see that A1 is equal to A3? That's one equation.
Yeah, sometimes
A2
it's,
is equal to 0. That's another equation.
yes,
I'm just visibly looking at
yes,
it. Kind of, you know.
Yep.
Not doing that.
Yeah.
Cheating.
Yes, you can do that. I mean, that's basically you're just doing substitutions before you, yeah.
Before you do math.
Mhm. Yeah. All right, are we done with this problem?
Yes.
Wrong, because what we're looking for is the acceleration of that point P. So, I mean, we're almost done because we have expressions for P, so let's just look for the simplest one. You know, what's the simplest expression we have for that point P? I guess it's this, negative 0.5 alpha 1, negative 0.866 alpha 1. And now we can plug in that alpha 1, and we get, so positive 1.1 and positive 1.91.
That's the same as acceleration at 2, which kind of makes sense because it's not rotating.
That's the same as the acceleration, what? Oh, yeah. Yes, exactly. Since it's not rotating, every point on this body is going to have the same acceleration. So yes, that's perfect. Yep.
Also, for the direction of the alpha vectors, because that 100 meters is applied clockwise, they're negative, right?
Yeah, you would expect, right, you would expect both of those angular accelerations to be clockwise. And we got that. So yeah, a lot of things make sense, yep. And I think it's useful. I mean, you can't always do this, but it is useful anytime you can make physical sense out of what's going on to think about it.
It's great when all the numbers match up.
Yes, it's really unpleasant when you spend half an hour on a problem and then nothing makes any sense.
Kind of like a sanity check.
Yeah, yes. Okay, that's it. So on Monday, so remember the quiz on Monday, and then, but also we'll just keep doing another problem or two like this before we go on to the next topic.